Hello, everyone. Welcome to the 22nd International Interactive Technical Talk. I'm Marc Ballouz, the president of ISSMGE. I'm going to introduce our speakers today. The talk is about residual tropical soils with TC107. And I will start by sharing my screen. So with us today, we have Professor David Toll from the UK. We have consultant Ahmed Chraibi from Morocco. We have Mwajuma Lingwanda from Tanzania, Africa. And then we have Fathiyah Hakim from Indonesia, from all around the world. This is what makes this talk special. This started since my presidency. I promised to bring together people from the industry and academia to discuss one specific topic, young and renowned, and it's interactive. I hope you will like it. This is episode number 22, as we said. We're trying to cover all the subspecialties of geotechnical engineering, and to control that, we're covering the TC technical committees of ISSMGE with about 40 subspecialties. So we're almost halfway through, a little bit more. Hopefully, I can cover all these subjects before I leave you and become past president. But for now, let's enjoy this 1 hour. I'm very excited to discover what you're going to say about the difficult and special residual and tropical soils. I would like to start by giving the floor to Professor David Toll. I will stop sharing, and David, you can start sharing.
Okay, can you see my screen okay?
Yes.
You are on. Yes.
Good, thank you very much. Good day, everybody. I'll start by providing an overview on some aspects of tropical residual soil behavior. So first of all, to remind ourselves what's special about tropical soils. If we look at a profile from the pole through to the equator across our planet, we can see that in the tropical region here at the equator, we have the highest temperatures and the highest rainfalls. And it's that combination of high rainfall and temperature that causes the greatest amount of chemical weathering anywhere on our planet. And so in the tropical region, we have a great depth of weathering due to chemical weathering. And because it's chemical weathering, it's taking place in situ without any transportation or movement of the soil. And so we end up with these tropical residual soils where they're weathered in place and have those particular aspects of behavior. Now, as geotechnical engineers and engineering geologists, we're very familiar with these engineering weathering grades, which identify the degree of decomposition or disintegration of the soil material from the fresh, unweathered rock through different stages of weathering until we get to the residual soil, where the soil has fully weathered down to a soil from its original parent rock. But we'll be talking about tropical residual soils, and for that we'll encompass the top 3 weathering grades, not just the true residual soil at the top, but also the completely weathered and highly weathered material. And those two grades we often refer to as the saprolite, which means it's a tropical residual soil that still has significant amounts of the parent rock present within the material. So it's those top three grades where it's dominantly soil that we'll focus on. And this is our conventional picture of the weathering grades. So we're talking about highly weathered, where more than 50% of the rock material is decomposed or disintegrated to soil, through to grade 6, where the soil has completely lost the structure of the original rock. So those upper three grades. But what we need to recognize is that not only do we have this breakdown of the rock to soil, but there are other things going on as the weathering process proceeds. And one of those is the mineralogical and geochemical changes that are also produced by weathering. And so I'll talk a little bit about Duchefort's classification, which has been adopted by the Geological Society of London as recognizing the different stages of weathering that take place in terms of mineralogy. And we start with phase 1, which is fersilitization, which produces smectite clays as the dominant clay mineral at that early stage of weathering. And that's the stage of weathering that we would find in the Mediterranean subtropical climates. So the least tropical end of the climate spectrum, if we like. And as we proceed down into the true subtropics, we'd move into ferruginous soils where we have kaolinites and smectites released by the weathering process. But it's only in the humid equatorial regions, in the tropics themselves, where we develop full ferrilitization, where kaolinite minerals are dominating along with gibbsite, which is aluminium oxide. And we'll also see that iron oxides get released as part of that geochemical change as well. So if we're thinking about the engineering behavior of these tropical residual soils, we need to focus on 4 things. So not just the amount of disintegration that's taking place, so that's a key aspect of the behavior. We also have to recognize these different forms of mineralogy, from those smectite clay minerals, the montmorillonites that give us so much problem in these vertisol materials, through so a couple of clay minerals that we'll talk about in a moment, allophane and halloysite, and then into the kaolinite type minerals that are present in the ferritic soils. But as well as that clay mineralogy changing, we also have iron and aluminium oxides and potentially other cementing agents released by weathering that can create a secondary cementing. And so we need to recognize that we might have a weakly cemented material that might develop onto a more nodular material through to a honeycomb and eventually to a hard pan or jury crust material where we're back to almost a rock-like material because of that secondary cementing. And we also have a structure due to the original parent rock, so the original bedding and jointing needs to be part of what we recognize within these materials, particularly the saprolites. So in very broad terms, we can sort of classify tropical soils into the broad categories of red soils, which are the ferruginous, ferrisols, and ferritic soils. And they generally contain low activity kaolinite type minerals. And that means they don't usually present major engineering problems. Of course, this is a very broad generalization, but very many red soils are actually good engineering materials. However, they may perform quite differently to our temperate sedimentary soils because we've got these strange minerals and we have the cementing agents in the tropical soils. And so we have to be a bit careful about how we treat them, and we can't always use our frameworks of temperate soils to interpret their behavior. I'll also just mention that laterite is a word that's been used to describe all sorts of different types of materials. And unfortunately, it's almost used to describe anything that's red. So that it can be a red tropical soil through to a really hard pan laterite ferricrete material. And so it's become almost meaningless in an engineering sense. So we have to be a bit more specific about how we describe some of these materials. And as I say, the black soils are often the real problem soils among our tropical soils. They form as part of the vertisols, early phase of weathering, and they lead to the very active clays, sometimes called expansive clays, and excessive shrinkage and swelling properties mean that they present major engineering problems. So just focusing a little bit on the red soils, the key aspect here is the presence of iron and aluminium oxides. That's Fe2O3 and Al2O3, the two common minerals, and they're often called the sesquioxides, and they have significant effects on the engineering properties. So they generally act as cementing agents, they can bond particles together, or they can coat groups of particles, hold them together. Sometimes they can exist as individual colloidal particles, and sometimes they act and hold water themselves. Another important interesting aspect of iron oxides is that although the insoluble form of iron is the Fe2O3, we also have iron 2+, the FeO iron oxide, which is actually a soluble form of iron oxide. And depending on the degrees of oxidation and reduction, we can move between these two phases. And so the insoluble ferric oxide, Fe2O3, if it's subjected to reduction, which can be the case if it's actually flooded and create anaerobic conditions, it becomes soluble, can move around within the profile. And then when the water drains and oxygen gets back into the soil, it reprecipitates and forms the ferric Fe2O3. So the iron can actually move between these soluble and insoluble forms. I mentioned the unusual clay minerals before, and two that we can focus on are allophane, which is an amorphous clay mineral, doesn't have a distinct crystalline structure, and it can hold a lot of water in its structure. And then we have halloysite, which is like a kaolinite type of mineral, but it has a tubular form rather than the platy form that we're used to with kaolinite and other clay minerals. The plates actually roll up into a tube, and again, water can be held within the tube. And so we have a lot of water holding capability for these clay minerals, but it doesn't necessarily mean they're bad materials. The water doesn't necessarily have a big effect on their engineering property. But both these clays are sensitive to drying. So if we dry them out, they change completely in nature. And we can have allophonous clays that when we often dry them, they change into a sand. They just behave like a sand. They lose plasticity altogether. And even if we add water back into it, it's an irreversible change. We can't recover that. So once we've oven dried it, we've changed the nature of the soil. And the same happens with halloysite as well. There's an irreversible change on drying. So both these changes in the clay minerals and also the sensitivity of the iron and aluminium oxides mean that many of our tests on red soils are very sensitive to the methods of preparation. So if we oven dry them before we test them, we change them completely. And so it becomes meaningless in terms of and if we mix them for different amounts, we get almost any result we want. So even simple tests like determining Atterberg limits or measuring the clay content, or even measuring a particle size distribution becomes very difficult in these cemented materials. And so trying to adopt something like a US CS classification often has very little meaning. So we really have to think about what these results actually mean in a rather different way to our conventional soil mechanics. Now, in terms of strength, this is some data from a granitic residual soil from Singapore. We're plotting the shear strength against normal strength stress for this residual soil. And we can see here the dotted line, the red dotted line, that would be the equivalent behavior of the soil if we were to remold it or destructure it and get rid of its cemented behavior. But what we can see is that at the lower stress range here, the cementing often gives us a higher failure envelope than the remolded soil. And we have a significant proportion of strength due to the cementing of the iron and aluminium oxides or other cementation agents that can take place in tropical residual soils. Now, that's cemented strength, a true cohesion due to a chemical bonding between the particles, of course, is something that can be destroyed by overstressing the soil. So if we consolidate it to high isotropic stresses or subject it to deviatoric stresses and high shear stresses, then we can actually break down these bonds. But if we operate within this region, the soil will certainly behave in a much better way than the equivalent remolded and destructured materials. And so it's very important that we recognize when we can make use of that cemented behavior and capitalize on it. And so just to round off with some conclusions, I would say that terminology for tropical soils can be very confusing. We find the literature from pedology, geology, and geochemistry often gives us a whole range of terms and things that we're not very familiar with in geotechnical engineering and can be very, very confusing. But for me, it's important to recognize that the engineering behavior of these materials is controlled by these four different aspects of behavior: the degree of disintegration through weathering, but also the presence of cementing agents, and then there's the sometimes strange mineralogy that we get within these materials as well as their overall structure. We also need to recognize that simple classification tests like Atterberg limits or particle size distributions can actually be very difficult to come up with simple representations of the behavior of the material. And we can sometimes get almost any number we want depending on how we do the test. But in very broad terms, I would say red soils can often be very good engineering materials. They behave quite well. But we can't always use the frameworks that we've developed for sedimentary soils to classify them. So we need to have this wider understanding. The black soils generally are problem soils. They're rich in smectites and certainly pose many engineering challenges. And so I'll just leave you with a slide of some of the classic texts that you will find useful if you need to find out a little bit more about the behavior of tropical residual soils. Thank you very much.
David, thank you so much for this broad view and definitions and clarifying for the viewers the different types of residual soils and clays. As I was practicing in Nigeria for many years, you could hear the engineers happy that they found laterite for the subsoil for roadworks, and they like it. They call it laterite and behaves like coarse grain. Now I can understand why, but you have to be careful also. So if you should be careful testing those using the classical ways. Are there any tests that should be done to determine those four different aspects? Is there like a specific thing you recommend when you find such soils? So how do you test, for example, their cementation or the the structure, all that?
Well, certainly, I mean, field descriptions are still very useful and very important for just being able to identify the level of cementing that's actually present, whether you've just got a weakly cemented, very friable material, or one that really has that hard pan, the strong lateritic behavior of some of the ferricretes. Certainly, geochemical testing is much more important in these types of soils. So knowing your iron and aluminium contents are very important. And mineralogy.
Like compaction tests and triaxial testing and all that is wetting, drying, expansion, consolidation. All these tests are useful to see if it's a good engineering material, right?
Absolutely. It's just, as I say, the difficulty sometimes is with the simple tests like the Atterberg limits and not trying to interpret too much from a set of simple tests that might be problematic.
May I
How about
add
the high?
something?
Yes,
Okay.
yes, Ahmed.
When carrying out Atterberg limits, for example, we cannot use the same sample for many tests. It's one sample for one test. The other time is that we just air drying at 50 degrees. We cannot go up to 105 degrees. And the laboratories, the engineers are not aware about that. When you dry it at 100 degrees and we use the same for, you get something which is unusable. Please correct me, Dr. And we have this problem in job sites and in the compaction tests. For example, you cannot use the same sample for compaction testing. And even the time of mixing, when you are dealing with the Atterberg limits, the time of mixing has an incidence on the results. So this is something which is very specific and the engineer should be aware about.
Excellent, excellent. That's why we have those talks to make people aware and careful when they deal with this material. Wonderful. Ahmed, the floor is yours if you want to share your screen.
Okay, thank you.
I like your French accent. Tu sais, moi aussi, je parle français venant du Liban.
And, okay. Do you
Floor is
see my
yours.
screen?
Yes.
Okay, let's go. So I'll talk about residual soils and dams. But first, I'll talk about the TC news as chair of this TC, which is almost sleeping, and then dams and tropical residual soils, and I'll talk mainly on case studies. Well, today our TC is 26 members from almost 20 countries. I was named as a chair 3 years ago by updating the terms of reference, and I organized a virtual meeting which attracted some interest, and Dr. David was present at this meeting, And then to create something to begin working, we propose two working groups, one on the in situ dynamic behavior of TRS, on which the documentation is very scarce, and the other on dams and TRS. They did not attract interest of the members. We got only one positive response for the in situ dynamic behavior. So we do not have at the present time any working groups, and I was even discussing with the secretary and the vice chair about resigning from this. Well, this is I'm still thinking about, because we should produce something as a TC of.
You cannot resign. I refuse your resignation.
Okay.
You have to activate it. Since
Well,
you are aware of it.
Thank you. I chair also the same TC on ICOLD, International Commission on Large Dams, where we managed to produce a bulletin after 4 years with a handful of active members. And so we could produce when we have people working, but when nobody is interested, that is somehow annoying.
We should fire and hire.
I'm trying, believe me. And at the present time, our TC is dormant. Well, let us see.
I'm happy also to tell you that we have the new bulletin for ISSMGE. Check it out. We already have 3 issues. Not a new bulletin, a new form, new format.
You know, the presentation of Dr. David is very interesting, and this is something that is found. He wrote many documents that are used in ICOLD bulletin, and his name is there among the references. Well, let us go to practical things. And here, this photo is from Xepyeong Dam in Laos, on which I had the opportunity to work after the fair. And we see here all these grades of weathering. We have the topsoil, we have the totally weathered. You have here silty sand. This is typical of when you have basalt as parent rock, saprolite with relict joints. All these elements. Saprolite is also used as construction material, and this is weathered basalt. And that meets what David just presented. And in this other site, Samandeni in Burkina Faso, all these photos are mine photos. Otherwise, I'll give the reference. This is in Burkina Faso, where we have very strong sandstone, and just on the top, you have totally weathered rock, and we are in this type. I don't know, David, if you're aware of this. Sure, this is Ruggieri 1960. We found this so interesting that we introduce it in our bulletin on dams. And this and the dry season, which is less than 3 months or more than 9 months, and the rain, which is 2,000 millimeters. And this is similar to the first slide you presented, but and here we have the Dury crust that develop, and we are in Xepyeong in this situation where we have more than 10 meters in this. We have almost 20 meters of this tropical residual soil, and in Samandeni, Burkina Faso, we have a few meters. And this is interesting. This is also another dam in Laos, Luang Prabang, under construction. That's this photo was taken in last October. And this excavation we see here, this saprolite, which with no totally weathered. We have here the topsoil, the saprolite, and then the strong rock which has been excavated by explosives. And we have also this type that has been found in a dam, where we have a problem of submersion and erosion in this. This is illustration of what David presented earlier. And this is a tropical material, residual soil, from a sandstone parent rock. We have here the saprolite, a clay joint, relict joint, which has an incidence on the stability. And here we have silty sand with some cementation. Otherwise, it will not be stable at this vertical slope. And here we are at the interface between saprolite, weathered, and the weathered rock, and with many coarse stones. And this is very fresh in excavation and erosion by water. And also with the duricrust, which is very hard, as we use it here in Komoe Dam, Burkina Faso. It is used as riprap, and we are in this configuration with the between 1,000 and 1,500 millimeters and 3 to 6 months of rain. And we have this, and this is we need explosive to get it as blocks. And this is another type where we have pseudokarstic voids. These voids are a result of there is chemical and erosion both together. And well, I would not say that it is canalicula. This is on Samandeni Dam in another part where the bedrock is not exactly the same as I showed you in before. And these are canalicula. This is a photo from Norte Energia, the Brazil. And Belo Monte is a very huge project with many saddle dams of 60, 70 meters high, only saddle dams. And we have this big canalicula of almost 30 centimeter diameter. We have another types. This is also in Brazil on a dam on which I'm working, which is under repair for repair works. And it is operating, and a trench downstream, we got this water coming from relict joints and from canalicula here. And the parent rock is gneiss, I think. And this is another Balbina Dam in Brazil, where we got this canalicula also, but the soil was enough strong to be treated by grouting by tuba manchette. The issue of permeability is something which is very important in dam engineering, of course, and the observation is that I have a problem with, the permeability of tropical residual soil encountered in unsaturated conditions is often higher than under permanent saturated conditions. You know, to build a dam, we have a river in the bottom, and we have saturation downstream, and in the flanks it's not saturated, and we observe this difference. And pump-in type permeability that we use, this is Lujon test, results in measured permeability values that are 1 or 2 orders of magnitude lower than the actual soil mass permeability. Smearing and plugging boreholes during drilling are the cause of these differences. And the recommendation is below water table pumping test is the most appropriate, and above the water table soakage and filtration test should be carried out in big excavation to get something which is appropriate. And generally, positive cutoff wall is the most appropriate solution to prevent piping and control seepage. Okay, and these are an examples that we carried out in Laos, Xepiang, Senamnoi, to get the permeabilities and to demonstrate that the permeabilities obtained here are 100 times higher than those obtained from the boreholes. This is the Saddle Dam D of Xepiang Senamnoi Dam in Laos at its completion in August 2017. This is some characteristics: 17 meters high, 770 meters. It is built using laterite, using compacted tropical residual, red tropical residual soil, and the foundation is made of residual soil up to 22 meters. And this dam experienced, this is the beginning of the collapse. It was not overtopped. We see here very dirty water and the water, clean water. And then this is when it has been completely washed away on more than 500 meters. And this is basalt as bedrock. And from this point to this point, we have 40 meters difference in height, and 22 of them are made of tropical residual soil, which is very, very heterogeneous. We got all types of material in this foundation, and with this erosion that you should, no stream exists before. We got a saddle here, and the stream that was created allows us to have a very nice picture on this foundation. And what happens is that the water tests were carried out by pumping in the presence of canaliculi that have never been evidenced, and the erodibility, sandy, silty lenses origins, whether it's like, well, that comes from this publication, and that correspond to the case that we experienced at this dam. The other is Komoe Dam, 1,170 meters.
Ahmed, sorry to interrupt you.
Yes, please.
On the previous dam, there was no cutoff wall underneath.
And no, because the water tests that were carried out, they led the designer to consider that the foundation was of low permeability. And for the other saddle dams, this is not the only one. They have 5 saddle dams. On the other, after this collapse, all of them, they carried out the positive cutoff by...
That's because they could not detect the canaliculi and the pseudokarstic features.
Well, because the engineers were not aware of the particularity of this type of soil. This is the main reason. And then we may find another reasons. But the main one is designer designed this with the Imperial College soils mechanics. So, sorry, David.
You cannot. No teasing.
Okay, let's go
ahead. Go ahead.
The other is also very interesting, because since 1991 and at the completion, we got 2 types on the flanks where we got the seepage and outcropping at the surface. And this is the left bank. Downstream, we have these depressions that occurred with a flow, with the subsidence of 0.5 to 1 meters, and we got something that was wrong here in this foundation of the dam. And as the seepage was increasing with time, the first time I've been there, that was in 2010, but for more than 20 years, we got the seepage flow, which was increasing. And then I will not go to the details, but the solution was to drive sheet piling here, and with the tuba-manchette grouting, and then compaction grouting. And when we conducted this compaction grouting, we got the absorptions of sometimes 10 cubic meters of mortar in just 1 meter of the hole. And that was really eroded. We got big erosion. Hopefully the strength of this compacted material, because this is compacted laterite, compacted red soil that has a very high cohesion and that withstand the deformations. We got deformations here, but we have not seen deformations there. So this is a view of the works, and this is the issue of colmatation of the filter by accumulation of iron oxide leached by seeping water from the reservoir. This is something that nobody talks about. And for dams, it's very important. And how I was led to this is working on dam in Brazil with of 50 meters high, with the vertical filter, which is almost plugged 50 years after its construction. And we got something like this. And even we are in low oxygen environments, a slow clogging process can develop due to the gradual oxygen introduction. I don't know, David, what do you think about this? But for dam engineer, this is very important. And the filter is the safety of the dam. And this is my last slide, is that meets what David just said. When you use correlations that were built for transported material, this is residual of an angle. This is very well known, and plasticity index. And we see that when you try to use it for tropical residual soils, you find something which does not, you cannot have any correlation. So we should think a lot about before. So thank you for your attention. That was my last.
Thank you, Ahmed. Beautiful presentation about the use of residual soils in dams.
And I think that final point was really interesting, Ahmed, about the oxidation and reduction actually allowing the iron oxide to move and change within the profile is absolutely critical in dams, as you say. And just to come back on your Imperial College note, you mentioned Peter Vaughan in that final slide, and I had the great pleasure of working with Peter Vaughan over many years during my time at Imperial College. And he knew as much about tropical residual soils as anybody I know, and didn't always apply the theory that comes from other parts of soil mechanics.
I was just joking.
I know, of course.
But you know, statistically speaking, I went to Google and tried to find out the documentation. We have almost 2% of the geotechnical documentation which is dedicated to tropical residual soils. 98% to transported soils. And because it's the code is very simple, the transported soil are in the north, in the people who developed all the soils mechanics, etc. And the other are in the south. And when we see that most of the dams that should be constructed are in Africa and in Asia, and where we are mostly dealing with this type of soil.
Nice remark. Mwajuma, are you ready? I think you're next. You're muted. Unmute.
Yes.
Yes, we
I'm
can hear.
ready. Yes, I'm ready, Mark, and thank you. Thanks for having me. We already have two very great presentations, so I hope I'm not going to spoil those with my presentation. And let me share. All right, just a second. Share. And share. Okay. So it took me on what to talk about in this session, mainly because I was questioning the relevance of what I'm going to say, but also the impact, and especially coming from Tanzania here, where we very much rely on these tropical residues, but unfortunately, we haven't done much when it comes to trying to understand the behaviors and how we can best apply them. So that was my hesitation. So then I asked myself, what do I wish to see coming from this side? And I thought I really wish to see more research on this area, and especially coming from Tanzania and Africa. Ahmed, your comment was quite relevant. We don't see much about these residue soils in literature. And for us, the ones who literally apply this material in everyday construction, obviously we have to do more. So I'm going to just speak my mind on what I think should be done when it comes to research that aims to support the use of tropical residue soils, and especially in infrastructure development. So, sorry, how can... Sorry, I have to minimize this. So the significance of residue soils. Without repeating much what has already been said, residue soils in form of natural gravels are a major source of road construction materials, and especially when it comes to construction of low volume roads, because we tend to rely on natural occurring gravels, which are easier to extract and apply. So for a country like Tanzania, which is geographically large, it is 13th largest in Africa in terms of geographical area. And we have about 70% of the population play a vital role when it comes to road development. Just to share a bit more about Tanzania and the road network, the size of the road network in Tanzania is approximately 145,000 kilometers, of which 36,000 are trunk roads and 109,000 kilometers are district roads. So what is the condition? We still are considered as a country with low road density of about 9.8 kilometers per each 100 kilometers squares. So as compared to our neighbors in East Africa, this is quite low. So we need more roads. And currently, more than 90% of the network is unpaved, and 6% or below 6% of the regional roads
Think we're experiencing low Wi-Fi. Mwajuma, turn off your video. Turn off the camera and we can hear you and see the presentation better. I hope you can hear me. Mwajuma, can you hear me? She's off. We'll wait 1 minute. Fathiyah, prepare yours. And we can come back to her slides. Just be ready. We'll wait 1 minute. I'll watch. If she's gonna try join again. Sometimes these things happen. She's back. Mwajuma, you're muted. Unmute, unmute. If you can hear me, you are muted. Keep the video off, but turn on your mic. Your microphone is off. Unmute yourself. Fathiyah?
Yes.
I think I'm gonna let you take over. So the floor is yours, and then we'll
Okay.
come back to the other presentation.
Okay, thank you very much.
Share your screen,
let me
please.
just-
Yeah.
Oh,
Yes.
oh,
Oh, there she is.
hello,
I
I'm
think.
back.
Yes,
Yes,
hello.
yes, finally.
Finally then.
Mwajuma, try to share
Um,
again. Be careful. Keep
yes,
your video camera off, but also keep the mic
yes,
on because you were
yes,
muted.
yes.
Go ahead. Can you share
I
your
don't know
screen?
why it was really difficult to. Yes, please. I'm sharing right now.
Okay.
Share screen. Wow. Share. Okay.
Yeah, I think your Wi-Fi is weak. That's why keep your camera off. Go ahead.
I think, yes, I think so.
Try
I'm
to
really
go
sorry.
faster
That
because we
is
lost
what.
time.
Okay, okay, let me go faster. So, to look into the significance of road material research, taking an example here in Tanzania, for low volume roads, approximately 70% of the construction cost is on pavement material and supply. And also, if you want to regravel, a typical replacement cost will be 60% of the maintenance cost. This shows that a reduction in material costs will significantly reduce the reduce the maintenance cost and development cost. And therefore, we need to do more efforts to make sure that we reduce the cost of maintenance and construction so that we achieve more of these projects. So, as I said, I will talk about areas that I think we need to do more when it comes to research. For example, characterization and classification of these tropical residue soils. The previous presenters hinted on the difference between in behavior between residue soils and the sedimentary soils. So standard material testing procedures developed through sedimentary soils may not be suitable for tropical residue soils. So an example of research could be trying to find some simple, the effect of some of these procedures. For example, oven drying of samples. Compare between oven drying and air drying, or light compaction vis-a-vis heavy compaction. We can start there, but how do we take into account the soil variability caused by the different degrees of weathering? Where do we put this in the equation of the whole characterization in trying to understand the residue materials? How to take advantage of technology development, for example, in terms of sampling or record keeping, detailed sampling, such as if we decide we can use GIS to store your reference, create spatial patterns of these materials to understand better, or estimating the reserve for tropical residue soils. As I said before, we rely on these materials. So just like any other natural materials, they will never grow back. They deplete with each use. With the advancement of the technology, we should be able to approximate their reserve and plan accordingly. We can start with their potential deposits. Typically, we take 50 kilometers radius within roads that we intend to improve. And then from there, because we know the network, which is already existing, then we can identify using our geological maps where we can locate the potential material, determine their quality and quantity, and therefore we have estimated the reserve. And we can still use tools, such tools as GIS, to create detailed spatial distribution map for these kinds of reserves. Or we can work on modifying test standards and procedures that are currently used. We know international standards provide universal framework for consistency and quality. However, some form of modification may come with some reduced cost of equipment, even time or expertise. It has been shown through research like use of in situ testing in place of we need to research to determine the correlation between empirical correlation between lab tests that we commonly use and these DCP tests. The use of materials. The available natural materials such as tropical quality standards for utilize these marginal materials. Without quality improvement, we already have some small research in 2020 demonstrated a total saving, a significant amount of dollar saved through substituting the recommended cement stabilization of marginal materials and replaced by mechanical stabilization in terms or in form of blending. Material properties. In our case, particular roads, we are designed using design. But thanks to research, it was possible to introduce low volume roads manual to be applicable for these kinds of this category of roads. This new cut in both technical and economical benefits. So you can one can demonstrate a significant saving in terms of material, for example, by just the approach in design. So we can do further research of these roads so that we can such procedures like field instrumentation as part of pavement monitoring can very well be applicable in collecting a large amount of data and then create global patterns which can be useful for decision making. And this is the last one, or even creating a database for soil properties. Experience is crucial in geotechnical engineering practice. We all agree on that, I think. But yet we do not have platforms to share data, even between institutions within the country. So you find two institutions working maybe in roads, but each one keeps their own data. So if we come up with an initiative to establish database of soil properties where and practitioners contributing to the expansion of and then consider methodologies like geotechnical engineering because it is support. So those are my expand the use of these materials, and these are some of the references that I passed through while preparing this short presentation. Thank you again very much. That's the end of my presentation.
Very, very good. Proposed research. I hope I can do some when I go visit you. Unfortunately, you were intermittently breaking the
let us
voice,
work
but
together.
I'm glad you had it
Really
all
welcome.
on the slides.
May I propose to share all this data on the website and
Yes.
particularly TC107. And then
Yes.
other people may take advantage of this and even enrich the information.
Okay. Sorry. Sorry, I didn't get you well, Ahmed.
Please,
Yes.
Marc, could you?
Yes.
Yes, he's suggesting that all this information should be shared, the data,
Yeah.
especially share it on the TC website,
Oh,
and people can take advantage, learn from it, and add on top of it. This data sharing is the new
oh,
trend that we should all follow. Geotechnical community is doing that.
sure, sure. Thank you. Yeah, thank you for
Please,
that comment.
please unshare so we can
Oh,
start with Fathiyah.
oh, sure.
Stop
Sure.
sharing.
Stop sharing. Uh,
And
oh,
Fathiyah, the floor is yours.
Okay, thank you very much. Let me share first. I don't know if I can
Go
share.
to the first slide.
oh, sorry. Did oh,
It's okay.
are you able
Let
to
me try sharing. Let me try sharing. Can you see my slide then right now?
Yes, go to the first one.
Okay.
Play the full screen. Here
Okay,
we
I
go.
already full screen. Okay. Okay, so today I'm
Lecture.
going to share about Indonesian tropical soil. So I did a little bit of research of um like what are the recent research in tropical soil in Indonesia, and here are some of the research that I found. And then I also want to share research which is actually numerical research in 2018 that I did with my professors. So first of all, if we talk about tropical soil in Indonesia, which already mentioned by Prof. Ahmed and Prof. David, that actually Indonesia is located at the equator. So it means that the rainfall is, we have a very heavy rainfall, even in some of our areas, such as here where I'm living in Java Island, and then some of the Sumatra Island, we have a wet dry season, which means that even though it's the dry season, we always have rain in that season too. So the main research in tropical soil is actually in geology and geological engineering, and also the agriculture. So it's very hard to find research about tropical soil related to geotechnical engineering. The very old one, and the one that is extensively used by a lot of engineers in Indonesia for the tropical soil, is actually done by Wesley in around 1900s, which is also mentioned in his book in 2010. Right, so it's already like around 10 years ago, but it's still being used. So first, what I found, the recent one is in West Lampung, which is in Sumatra Island in Indonesia, by Iqbal P. et al. So I think this is part of his research for the volcanic red clay. So the clay is actually red but a bit yellowish, and it when using the Atterberg limit, it was found that the soil falls into the MH, which is the silty with high plasticity, and it's actually produced from weathering volcanic rocks with felsic mineral composition, and the minerals were kaolinite, halloysite, and montmorillonite. So the authors suggested that actually when we classify the volcanic red clay, especially in this West Lampung, Sumatra, rather than just using the Unified Soil Classification System, which is USCS, the authors also suggested that we use what we call that they called revised soil classification system. I don't actually know the specification for the RSCS. It doesn't, the author doesn't really specify it. And lastly, also use the XRD to actually determine the mineral that are dominant in the clay. So this is used to determine the interpretation. Because this is for geological and agriculture, it is very important for it to evaluate land use. And then the next one is in Maluku, which is in Halmahera. They call it lateritic soil. It has 3 different iron content which were stabilized by quicklime. The laterite soil is actually classified as CH, which is clay with high plasticity, and it is dominated with Mount Morillonite, elite, and has ferromoxide content. And it was known that when stabilized with quicklime, the higher the iron content, then it will give a higher increase of strength. And then in Kalimantan, laterite soil from South Kalimantan by Rusdiansyah et al. At 2021. It was tested for residual shear strength, but the residual shear strength was tested with the addition of coarse sand and low plasticity clay fractions, and also the effect of wetting drying cycle. So the authors also added the wetting drying cycle for the laterite soil with the addition of the coarse sand and the low plasticity clay. It was found that with the addition, it will give an increase of residual shear strength perimeters, and additionally, the wetting drying cycle will give a lower peak and residual shear strength for the soil. And then in West Java, actually, there are a couple of research for the tropical soil, especially for the red clay in West Java, because there are a lot of red clay actually in Java Island. I will show it later. So in Cikampek, Cikawang, and Lembang in West Java, they see the difference between the undisturbed and the remodeled unconsolidated undrained axial shear strength, which then showed a low sensitivity, which the values were 10%, 12%, and 40% consecutively. So this is one of the main research that was done in Wesley. You can see here is 1973. It's already very outdated, actually. And these are the couple of red soils in Java, which are the latosol, latosan, andosol, and andosol. So this is still used as a reference for a lot of tropical soil in Indonesia. And again, I already said that there are a lot of landslide that happens in Indonesia, especially actually in Java Island. So in Java Island itself, this is my data from the BNPB, which is the National Board of Disaster Management. At least around 150 landslides from 184 landslides were due to rainfall during the 2013 to the 2016 period. So that's a lot of landslide because of rainfall. And mostly, actually, when I saw the pictures were red clays, right? So it's something that always happens in the rainy season. Okay, so one of the research that I did for the tropical soil, which is actually the red clay, is that I got around 31 data of axial consolidated undrained in Jakarta and also Depok, and then I put it in this attribute limit by Wesley in 2010. I focused it on the tropical red clays here, which is the halosite. And then afterwards, I put it as a probabilistic function in the SOAP W, and I put the rainfall in the SIP W with a couple of geometries. And this is one of the rainfall that I got in University of Indonesia throughout July 2014 to March 2015, which is I divided into 36 intervals of 2-hour rainfalls, and then these are some of the results that I got. So the steeper the slope, actually we have the greater probability for the slope to fail, and that the most significant change is actually during the first rainfall, because this is the advanced type of rainfall, which means that the highest rainfall was seen in the first 24 hours rather than the 36 and the 72 hours. And this was when we saw it as a different height at different angle of the slope. And here we got the pore water pressure at the top and also the bottom of the slope, which we can see here that at the upper part of the slope, there's a 0 kPa water pressure. So when I analyze this, it is mostly means that the soil is saturated enough, so there are a lot of surface runoff, and because of that, mostly the landslide will be done by erosion on the top of the slope rather than deep-seated slope failure. Okay, so lastly, for future research, it was intriguing that I saw the presentation before for this that when we talk about tropical soils, it's not only limited to red clay, but actually in Indonesia, when we talk about tropical residual soil, a lot of people will mention it as laterite and red clay. So it's actually a little bit mind-blowing for me that the definition of tropical residual soil is not only limited to that. So maybe there are a lot of research that can be done here in Indonesia because we have a lot of tropical residual soil here. And fortunately, the residual shear strength research is actually gaining a lot of attention in the current research environment. But I think mostly it's clay shell, which are a bit of what we called here a problematic soil, because there are a lot of national project for roads here that are happening in clay shell soils, and we have also pit soils and etc. So because of that many problematic soils, these red clays are actually a bit left behind, because we always say it, this is a very good material. That's why. These are some of the references that I found for the current research of tropical residual soils in Indonesia. Terima kasih. Thank you very much.
Wonderful. Thank you, Fathiyah. So I was comparing the first slide of David and trying to understand that laterites are around the equator mostly, and that's why in Tanzania it's close to the equator, and Indonesia close to the equator. You have such material. Correct me, David, if I'm wrong. Those residual material exist there.
Exactly. I actually just have a map of the distribution that I can just quickly flick up.
It would be fantastic to go back to international. Yes.
So there's the picture. So of course it's the zone around the equator where these things dominate. So South America, across the middle of Africa, and across into where Fathiyah has just been talking about. But we do get other soils, the earlier stages of weathering in a little bit more northerly regions as well. But certainly the real ferrolytic soils are dominated around the equator.
Yeah, excuse me. When I see in the North Africa this ferrolytic soil, they are not tropical residual. They are residual soils, but not tropical. And so far, I didn't found any map that provides the real location of tropical residual soil, even they represent more than 25% of the surface covered of the dry surface of the earth.
Absolutely.
You have to go test all around the world, Ahmed.
Well, I work in many parts, and in our bulletin that I talked about for ICOR, the International Commission on Large Dams, we try to place a map. You have the map of Fook that dates from the 70s, but this is pedological, not the geological map where these soils are. And so far, there is no one. At least I didn't found.
I can try to help. I've been to 42 countries in 2 years. I can bring samples with me.
Okay.
It's work in progress.
And
That's why Mwajuma and Fathiyah said further research.
for Fathiyah, I would suggest to look at what have been done in Colombia. They are in mountainous region, and they have this tropical residual soil, and they have many instabilities. And they carried out a lot of work. So there is something to find there. Well, I know more about what they have been done in the dam reservoirs with these steep slopes, but it could be interesting for you as a reference.
Yeah.
I think the other important thing is that when we're talking about tropical residual soils in this part of the world, many of these soils are unsaturated, as Fathiyah has said. So there's definitely an element of unsaturated soil behavior that we need to bring in to understand as part of this as well. And the fact that Fathiyah was mentioning that many of these landslides are actually shallow failures, that's very typical of unsaturated soil conditions where infiltration from the surface causes that shallow slope failure. And we see those across Asia, in Singapore and Malaysia, as well as in Indonesia. So a very, very typical aspect of behavior that's really controlled by the unsaturated soil behavior rather than any of the other factors.
Yes, yes, that's right.
We ran over time. Exciting. I want to thank you all and conclude this talk, IITT number 22. Thank you very much to all of you for the time you put in preparing, for being with us. This is being recorded. It will be published in the coming week or two, and you will get notified. And hopefully all our viewers will like it. Thank you so much, and have a wonderful rest of the day or night, wherever you are around the world.
Okay, thank you. Bye-bye.
Thank you very much. Goodbye.